Hello, and welcome to our listeners around the world. You're listening to JAMAevidence, our podcast series based on core issues in evidence based medicine. Today, we're discussing the use of pattern mixture models for assessing the potential impact of missing data. I'm your host, Dr. Roger Lewis, Senior Statistical Editor for JAMA and editor of the JAMA Guide to Statistics and Methods series. I'm also a professor of emergency medicine at the David Geffen School of Medicine at UCLA and a senior medical scientist at Berry Consultants. I'm here with Professor Roderick Little. Dr. Little, could you go ahead and tell our audience a little bit about yourself?
Yes, hello everybody. So my name is Rod Little. I'm Emeritus Professor of Biostatistics at the University of Michigan, and one of my main research interests is in the analysis of data with missing values.
So, Rod, in the article that you wrote for JAMA, you talk about the use of pattern mixture models for assessing the potential impact of missing data on the validity of the estimates of treatment effects that we get from randomized clinical trials. So let's start at the beginning and review for our listeners what are missing data and why are they so important?
Yeah, so missing data are just things that we were trying to record during a clinical trial or a study that didn't get measured. Perhaps people dropped out before the end of a study, so the values were missing, or sometimes you can have missing values for intermediate variables or background variables. So it's quite common to have missing values or gaps in a data set. The importance in a randomized clinical trial is that if you have missing data, particularly on outcome variables, then that can mess up the randomization. So it has the potential to lead to biased estimates of treatment effects. Statistical analysis can handle missing data, but it has to rely on some kinds of assumptions about the distribution of the missing values. And if those assumptions are not true, then the treatment effects can be biased. For that reason, although I like to think about methods for analyzing missing data, actually the best thing is to try and avoid it if it's at all possible.
I think that we all have observed that as much as people try to minimize missing data and missing outcome data, particularly in clinical trials, it's almost unavoidable, certainly in trials that involve large populations or following patients over a long period of time. You mentioned that many statistical approaches make assumptions about the distribution of the missing values, meaning what would have those values looked like had we been able to observe them? So let's talk a little bit about those possible assumptions. Let's start with the simplest and go to the most challenging.
Yes, Don Rubin, who's done a lot of work on missing data, back in the 1970s, he defined three categories of missing data. Missing completely at random, meaning that it's like throwing at a dartboard. The missingness is not related to anything. Missing at random, which is an assumption that missingness can be explained by variables that you have recorded in the data set, but doesn't depend on the value of the variable that's missing. And then missing not at random. And one of the reasons for this work is that most of the methods for handling missing data in clinical studies assumes missing at random. That is, it assumes that the things that are missing can be explained, missingness can be explained in terms of variables that you actually have recorded. That's an assumption, and in some situations, it's not necessarily true. For example, you could have a situation where somebody drops out of a study because they have side effects from a treatment, and those side effects have an influence on the value that would have been recorded. If that's the case, then it's quite likely that this is not missing at random, and so a method that makes the missing at random assumption is potentially going to be biased.
And just to be concrete, a standard approach that we see and often encourage in the analysis of clinical trials is multiple imputation, where you fill in the missing values with a number of possible values that might have been seen, taking into account what else you know about the individual patients and which of the assumptions is required for multiple imputation to work properly.
I like multiple imputation. I think it's a very useful technique. The basic idea is that you have an analysis method that generates a predictive distribution for the missing values. What are the set of values that could have been observed, and what's the distribution over those values? under that model. Then multiple imputation, then plugging in the best estimate, it draws from the distribution, and then it does it more than once. So you create a set of filled-in data sets that have different values imputed for the missing values. Once you have this set of filled-in data sets, you then analyze each of them and then combine the results in a way that gives you statistical inferences, p-values, confidence intervals, and the like, that reflect the fact that there's uncertainty in the missing values.
And just to be clear, the way we usually see it implemented, meaning to analyze data for a clinical trial, but not using the pattern mixture approach, does require the assumption of missing at random. Is that correct?
So the answer to your question, Roger, is yes. Most of the multiple imputation approaches for handling missing data using standard analysis models assume missing at random.
Rod, in your article, you give a very nice concrete example of a situation in which the outcome data might be missing at random or conversely might be missing not at random. Can you go ahead and explain that example, please?
So the missing at random assumption for a general pattern of missing data is a little bit hard to understand. So I'm going to explain it in a relatively simple situation where you just have missing values on an outcome variable in a clinical trial in a longitudinal study. And you have values of a baseline variable and time one variables are fully observed, but values at time two that are missing for patients who dropped out. In that situation, missing at random implies that missingness of the outcome at time two is allowed to depend on the outcome at time one and baseline variables because those are fully observed, but can't depend on the outcome at time two. If it depended on the outcome at time two, then it would be missing not at random.
So the key idea here is that if the data are missing not at random, you actually would need to know the value you haven't seen in order to understand why it was missing.
Yes. So if you could assume missing at random, then there's a set of possible predictions for the missing values at time point two, and you could assess that distribution using the observed data. So you can take the cases that are observed at time point two, they have a distribution, and then if you condition on the information at times baseline at time one, then you can use the observed data to essentially predict what would happen for the missing cases. If you're missing not at random, however, the distribution for the missing cases is different from the distribution from the observed cases. So then you have a problem.
So in your article, you focus on the use of pattern mixture models in order to address this more difficult situation where the actual value you didn't observe influences the chance of it being missing. Let's break down this name pattern mixture model. So what do you mean by pattern and what do you mean by mixture?
A pattern mixture model means that the patient's data are classified by the pattern of missing values, and then the distribution of the study variables is modeled within each pattern. In the simplest case, where missing data are confined to a single primary outcome, say Y, then there are just two patterns. There's study participants where Y is observed and study participants where Y is missing. So you essentially have your observed cases and the missing cases. So then you model the distribution of Y for cases that are observed and cases for a missing. And under missing not at random, that distribution is going to be changed from the observed cases. The term mixture is used because once you've done this separately in each pattern, you then have to mix the information across the patterns to get an overall treatment effect that applies to both observed and missing cases.
And one of the strengths of this technique is that it allows you to consider different degrees of deviation from the missing at random assumption. Can you talk a little bit about how that works? How do you sort of mechanically test out what would happen depending on how far afield your data have fallen from the missing at random assumption?
So I said if we're going to do multiple imputation, we need a predictive distribution for the values that are missing. Under missing at random, you get that predictive distribution from the cases that are observed. Under missing not at random, however, we shift that distribution in some way. And the simplest and usual way we do it is to assume a shift in the mean of the distribution, so it gets shifted one way or the other. So the article talks about this delta value. The delta is how much the mean of the predictive distribution is shifted from those for the observed cases. So the idea is then to basically choose different values of delta and then decide whether the shift under which the difference in the treatments goes away is unrealistic or unlikely. So you're looking at plausible values of delta and see how much the results of the study changes for these different values of delta.
So let me see if I can summarize this correctly. You have a result from your primary analysis in which you may have, for example, filled in the missing data with multiple imputation. In order to then evaluate the robustness of that result, you do multiple imputation separately within the different patterns of missingness. And for some of them, you shift the values you impute, combine the complete cases with the cases in which you filled in the missing data, and see whether the total result from the combination of all of the cases now deviates qualitatively from the result you got from the original analysis. Is that a fair summary?
Yeah, I think you probably said it better than I did. So
Okay, well, that's very generous. So this approach doesn't tell us what the right answer is under missing not at random, but it helps us understand how much faith we should have in the result that we got under the more naive strategy of assuming missing at random.
correct.
So what are the limitations of this approach? Where does it break down, or what should readers look for when this approach is used?
Yes, so I've talked about this shift parameter if we're looking at a shift in the mean of the predictive distribution. Well, there are a lot of possible shift parameters. If there's only one variable that's missing, then perhaps you can talk about a shift for the predictive distribution of that variable. On the other hand, the shift might vary for different types of missing data. In fact, in some ways, I think that's quite a useful thing. For example, there may be some types of missing data, people drop out because they went out of town or something, that might be plausibly missing at random. But then there are other types of missing data, like from side effects and the like, that are plausibly not missing at random. So it's actually a good idea to look at why things are missing, because sometimes you can tweak the missing at random assumption depending on what kind of missing data are. Then I've talked about a shift in the mean, but maybe it's just shift in the spread of the distribution. And then if there are many variables that have missing values, then you can imagine each of those variables has shift parameters. Then it becomes an unwieldy thing to vary all of these parameters. So there are limitations in what we can actually do. And what we try to do is focus on the main primary outcome of the study and the main deviations that we're worried about. So limit it to one and perhaps two parameters. What's often done, and this is actually done in the example we're going to talk about, is to make the new treatment in some senses look worse by assuming that this shift makes the outcomes in the new treatment group worse while not changing the outcomes in the control group. So the delta for the control group essentially becomes zero. So you try and become more conservative, and then you see, well, how conservative do you have to become before the treatment effect essentially goes away? So we have these different values of delta, and let's suppose that we were doing the analysis to make the treatment look worse. So as delta gets larger, the treatment effect goes down. If we do that, then as we increase delta and the treatment effect goes down, then the significance of the result gets less and less significant. So there is a point at which you lose statistical significance at some conventional level, like the 5% level. That value is known as the tipping point. And since it's hard to determine what the good values of delta are, what some people do, and I think it's quite reasonable, is to seek the tipping point at which the treatment effect essentially becomes non-significant, and then you can argue as to whether that's a plausible value of delta. If it is plausible, then the study's results become more questionable. On the other hand, if it is unreasonable, then the results are relatively robust. And in that situation, the study is still looking good.
And just to put this back into clinical terms, when we say making delta bigger, what we're talking about is assuming that the outcomes that are missing are from patients who did systematically worse than we would have otherwise expected based on everything else we knew about those patients. So it's the degree with which the data were not missing at random, but instead the unseen outcomes were systematically worse than what we otherwise would have expected.
Yes, that's right. And I think in some settings, it may be reasonable to believe that the people that drop out are perhaps dropping out because the treatment is not so effective for them. So, in that sense, it's kind of a rational way of doing the sensitivity.
So, in your article, you use a specific example of the use of this technique. So, let's talk a little bit about that. So, can you describe the study in which this approach was used and what the authors did and reported?
Yes, the application, which is a paper by Davis et al., was looking at treatments for PTSD, post traumatic stress syndrome. So there's a primary outcome measure for PTSD in the study, which is called CAPS-5. Those of you who work in this area are probably familiar with it, where higher scores indicate worse symptoms. So this outcome measure was completed at baseline and at a variety of weeks, 3, 1, 3, 4, 6, 10, and 12 weeks. Then for people in the treatment group, brexpiprazole plus sertraline, the completion rates for the full study up to 12 weeks were 137 out of 214, or 64%. And in the control group, which was sertraline plus placebo, 113 out of 202 participants, or 55.9%, completed the study. So there's missing data because they dropped out of these two groups. The primary analysis was based on a mixed model for repeated measures, which is a very common method for handling longitudinal data. And that is a method that does assume missing at random. A sensitivity analysis, which is in the description of the method in the original paper, was applied to assess the potential impact of missing not at random missing data. And the impact of departures from missing at random was assessed by progressively increasing this delta value that we've talked about earlier for the dropouts in the treatment group, not in the control group, from 0 to 100% of the expected treatment difference, which was 5 points. So this is a case where the delta is being applied only to the treatment group to make the treatment group look worse than assuming missing at random. So then they display the results of looking at these different values of delta. And when the delta is 0, that's the missing at random model, the treatment effect was minus 5.45. I won't say what that actually means clinically, but it has a p-value of less than 0.001, so very highly significant. When delta was equal to 5, which is the largest value of delta they looked at, the treatment effect was minus 4.04. A lower p-value because the treatment effect has gone down, but still a p-value that's less than 0.01. I mentioned this tipping point. The delta tipping point at p equals 0.05 was 8, or 1.6 times the expected treatment difference. So this is a large treatment effect. So based on that sensitivity analysis, they concluded that deviations from missing not at random were unlikely to explain the difference in the treatment and control groups. So the study remained robust to the outcome.
So, given this result that they obtained, how would you interpret that overall?
So the general conclusion in the Davis et al. Article was that the treatment effect is too large to be attributable to bias from missing not at random. So the treatment effect sort of held up to this sensitivity analysis. Although, as I state in the article, as with any analysis of this kind, they're only looking at a very limited form of deviations from missing at random. And the choice and values of delta parameters are subject to uncertainty and potential disagreement. In fact, what actually happens in practice is if drug companies are doing studies, then the FDA or the regulating agency will look at the protocol for the analysis and agree to a particular form of analysis prior to the study. As many of your readers know, it's always a good idea to write down ahead of time how you're going to analyze the data. Anyway, it does add to uncertainty, so there could still be controversy even after the most careful of these types of analyses. So I think perhaps because of that, it's worth stating what I think I said at the outset, is it's better not to have missing data because missing data adds to the uncertainty as to whether a drug is good or not.
So, Rod, what do you think the take-home message is for our audience?
The first thing I want to say is that missing data is a problem when you're doing clinical trials, because if you have a lot of missing data, then it creates uncertainty about whether the treatment effect is valid or not. So the first thing to say is try not to have missing data. So design studies or conduct studies in a way that limit the amount of missing data. The second point is that most of the methods for handling missing data in clinical trials make a fairly strong assumption that data are missing at random, which essentially means that the cases that are missing, the distribution of missing values, looks similar to those of observed cases after taking account of the variables we have observed. So when that's a questionable assumption, this method comes into play because it's a relatively straightforward way of assessing the effect of deviations from this missing at random assumption. So you do what we call a sensitivity analysis, where you vary this difference between the respondents and missing cases and observed cases, and see whether the treatment effect goes away for different values of this difference. So pattern mixture models are useful for that. People don't like sensitivity analyses very much. I'm not sure if I should say that, because they don't want to have to look at lots of different results. However, this is a scientific way of assessing robustness to deviations from missing at random, and so I think it's a useful method.
I am Roger Lewis, and I've been speaking with Professor Roderick Little about the use of pattern mixture models to assess the robustness of clinical trial results to data that are missing not at random. You can find a link to his article in this episode's description. This episode was produced by Daniel Nassisi at the JAMA Network. To follow this and other JAMA Network podcasts, please visit us online at jamanetworkaudio.com or search for JAMA Network wherever you get your podcasts. Thanks for listening.
This content is protected by copyright by the American Medical Association with all rights reserved, including those for text and data mining, AI training, and similar technologies.